All right, so we're going to start with our catalyst here. And we have a sodium carbonate solution combined with a calcium chloride solution. And we are going to start with polonium. And so you are going to give us the balanced formula equation, and I'll write it down. All right, go ahead.
Na2CO3.
Okay. What else do I need there?
Aqueous.
Okay, good.
Plus CaCl2 aqueous.
Good.
Results in 2 NaCl aqueous.
Okay.
Plus CaCO3 solid.
Okay, how did you come up with the idea that the CaCO3 would be a solid?
Because of the book.
What did you do?
I don't have it, but it says like carbonate is insoluble unless it has
certain other exceptions, right? Okay, good. So we see that most carbonates are insoluble. We look for exceptions. In this case, this was not one of them. And so it stays insoluble. So we put an S on it. Very good, polonium. You did an excellent job. All right, so let's see if strontium can do the total ionic equation. And talk me through that one.
Na2.
Okay, Na2, if I put a little 2 as a subscript, then that is kind of indicating that it might be bonded together. But we want to indicate that the water is surrounding each of our ions and it separates these ions out. So what else could I do?
Coefficient?
Yeah. So we'd put a 2 there instead of as a subscript, right?
Mm-hmm.
Good. And then what else does Na need?
Plus
and
aqueous.
Excellent.
And
okay, keep going.
I said plus CO or 3CO, or no, would it just be CO3?
Yeah, so this one's tricky, right? Because you see that 3, but remember that this is a polyatomic ion. And so this is the one that you keep together in a little group, right? So we don't separate those guys out and put the 3 in front of the O. This stays together as a group because it's a molecular group that's acting together as an ion. Okay, what charge do I need there?
2 negative.
Awesome. And then what else do I need?
Aqueous.
Excellent. Keep going.
Plus Ca2, like charge of 2 plus.
Good. 2 plus. 2. Good.
Aqueous.
Nice.
And then plus Cl or 2Cl.
Good. 2Cl.
Negative. Aqueous.
Excellent. Then?
2Na. Positive. Aqueous.
Good.
Plus 2Cl.
So good.
Negative aqueous.
Excellent.
And then plus CaCO3 solid.
Awesome. Good job. All right, so we broke everything down into the component ions that we had. So that was really good. Good job, strontium. All right, now I have our final net ionic equation. Did I give points to that first one? Did I? Okay. All right, net ionic equation is going to go to rubidium. All right, net ionic equation to rubidium. What you got?
CO3 2 plus charge aqueous.
Okay, CO3 to what?
Plus.
To minus, right?
2 minus.
Because the carbonate's a negatively charged ion.
Plus Ca2 plus aqueous.
Okay, good.
Results in CaCO3 solid.
Good. Excellent job with the solid after that. And so that net ionic equation made me get rid of all of my what type of ions? I kind of got rid of them all. Starts with an S?
Spectator ions.
Spectator ions. Good job. Yeah. So get rid of all those spectator ions when you're making your net ionic equation. You only include the things that make that solid. Great job. All right, does anybody have any questions? Okay. Let's go ahead and then move on to, yes, question.
For the balance equation, the NA has a 2 like in front of it instead of a coefficient. Like, does that change once we go to like a total ionic equation and then why?
Yeah, so the question is, why does this 2 here as a subscript turn into the 2 as a coefficient?
Yeah, like I understand the part of like it's not like a compound, but like not really.
Okay, so I want you to think about if I had 2 NAs, the idea would be that they are somehow bonded together. Okay, this would be an Na2. Whereas if I had an Na that was surrounded by a bunch of H2Os, right? It's just a bunch of H2Os. And then I had another Na that was also positive, but then surrounded by a bunch of H2Os. That's what we are trying to demonstrate by 2Na, where you have 2 separate NAs surrounded by waters instead of a bonded Na to another Na. Does that make sense? So the subscript is telling us that these things are bonded together in some sort of complex structure, whereas the coefficient tells us, hey, we're separating these things out into their separate ions. Does that make sense? Yeah? Okay, good question. You are Indian, right? Good question. All right. Any other questions? All right. Let's go ahead and go on to, I'll give you a different slide. Go on to our objectives for our 13.2. All right, so we want to look at how solutes affect the freezing and boiling points of a solution. And specifically, we're going to go into what is the difference that we have in the effects if I have an electrolyte versus a non-electrolyte solute. Okay. All right, so we are going to talk about colligative properties today. And this is one of my favorite lectures because I know that right after this lecture, I'm going to have some ice cream sometime soon. So the colligative property lecture is about particles and how the number of particles can affect the freezing point depression. And that is how we're going to make ice cream on Monday. So on Monday, if you want to bring in your own types of ice cream toppings or accoutrements, you can. We are going to make plain vanilla ice cream, but if you want to add something to your ice cream to have some sort of extra pizzazz, you are welcome to do so. But that is going to come up, and so I love it. And so this is a fun lecture for me because I think about ice cream. All right, so our colligative properties. These are properties that are going to be affected by just the number of particles and not the identity of the substance. So if I have 2 particles versus 3 particles versus 4 particles, it's the particles that matter, it's not the identity. So in other words, it doesn't matter if it's sodium, fluorine, chlorine, calcium, magnesium. We don't care what particle it is. All the particles have the same effect. That's what a colligative property is. It doesn't matter what the identity is, it just matters the actual particle number. So it's all about concentration. And so your concentration of your solute particles is going to be the thing that determines your colligative properties. And of course, the properties that we're probably going to associate with today is going to be your freezing point depression and your boiling point elevation. Okay, so that's what we're going to look at. It's, for the most part, it's a pretty direct relationship. You've got a very definite correlation between the number of particles and the effect that you're going to be dealing with. So if I add more particles, I'm going to get more freezing point depression, or more particles, more boiling point elevation. And so it's pretty direct. Now, once you get to a certain point where you added just so many particles, it eventually nullifies and you don't have any greater effect once you've maximized your number of particles that are kind of getting in the way. But it does kind of increase pretty directly as you start this process. Any question on colligative properties? Okay. So let's talk about our freezing point depression. If you think about what we have here, in this example, we have a compound that has combined very nicely together in a very organized structure. So you can imagine all these little pieces are all grabbing hands, holding hands, and making a nice, strong ice crystal. Okay, so imagine these are all little water particles, and they're all coming together and making a nice ice crystal. There had to be a bunch of intermolecular forces that were involved for them to do that. Okay, so what a solute particle can do is a solute particle can kind of get in the way. And so if we look at this one here, we kind of have these little triangles getting in the way of all those little circles holding hands. And so those little triangles are preventing the little circles from grabbing onto each other again. And of course, if this grabbing onto each other kind of thing is what we mean by freezing, and we're actually creating a crystal by freezing, now I can't create that crystal very easily if there's something in the way. And so that's what we're seeing here on the second diagram, that we have things that are getting in the way with that crystal forming. Now you'll notice that we call this freezing point depression. And the more solute particles you have, the lower that freezing point gets. The idea here is that it's going to take less energy to separate these little guys together. And so it's going to lower your freezing point or your melting point, if you want to talk about it either way. Now, why is it incorrect then to say that when I pour salt on ice, that I'm melting the ice with salt? Why is it incorrect to say that? We'll start with indium. I'll get you a little microphone.
So how I kind of see it is that instead of you like melting, I feel like you're not really like going, like, yes, you are going through a phase change, but it's like more chemically involved, and so it's like breaking down like that substance by introducing a different substance, therefore having like a different like identity overall, and that new identity has different properties that can seem like as if it were melting.
Okay. Good logical talk through there. Let me ask you this as a follow-up question. Am I adding heat to the ice when I'm adding salt to the ice?
No.
Okay, so usually when we talk about melting something, we are melting it by adding what?
Heat.
Yeah, so if I'm not adding heat, am I melting the ice by adding salt? No. Okay, so we want to talk about then what is adding the heat. Do we have another guess here? Looks like we do. Let's see if polonium can help us understand what is melting the ice then.
I think the salt turns the compound from compound A to compound B, which lowers the freezing and melting point. And
okay.
The outside temperatures would just melt it.
Okay. Good guess. I'm going to say, congratulations on discovering smelting, by the way. I'm going to say no, though, on that guess. Why don't you pass that to Moscovium, and let's see what Moscovium has to say.
The new solute like makes it easier for the ice to melt and like outside, or like makes it easier for the ice to.
Where is the heat? The question is, where is the heat coming from that's melting the ice? If I'm not adding heat and yet the ice is melting, where's the heat coming from?
The pressure.
No.
Outside.
Good guess, though. All right. Anybody else want to try this one? Pass it back to Bismuth. What do you think, Bismuth?
Would it be because introducing compound B into compound A disturbs the IMFs, which releases heat because since there's a greater distance and a greater volume, the temperature would also have to increase?
Interesting. I like how you're thinking about the interrelationship between those things. But no, the first part you said was really great. You're reducing the intermolecular forces, being able to attract it and pull them together. But we still haven't identified where the heat's coming from. Let's see if germanium can answer that question. Go ahead and pass that back. What do you think, germanium?
I think that since like the particles are like the the molecule B. Wait,
where's the heat coming from?
Yeah, I don't know.
Okay, let's go with arsenic.
So since it's like just adding more like particles overall, does that mean like there's going to be more collisions because there's like more particles?
Love how you're thinking about collisions. You do have more particles. Not where we're going. I'm okay with the idea of collisions here, but I don't think it's a source of significant heat that we would experience melting with. Okay, so I like what you're thinking there, but not where we're going. Anybody else? Yeah, go ahead. Are you, yeah, tellurium? Why don't you pass it out? What do you think?
The addition of an electrolyte?
No, so the electrolyte is basically, in this case, we're probably talking about the electrolyte is like the little triangles, right? That's your compound B. Good guess, though. Go back to bismuth. Let's see if you can get it this time.
Would it be because compound B, since it's an ion and it breaks down, the released energy from the breaking of that ionic bond travels into compound A, which increases heat?
Okay, so I definitely like how you're thinking about if we are not going to have if we have a broken up bond, what causes bonds to break though typically is, energy, right? You need energy to break bonds. And so that's not really giving us the source of heat. It's actually would be more of an endothermic process, right? Than an exothermic process. So, but you guys got to kind of open up your minds to something a little bit bigger in terms of, like, let's just imagine I've got some ice and it's outside and it's on my sidewalk, okay? And I pour some salt on it and it starts to melt. The salt is not melting. It's not getting energy from the salt. Where could it be getting the energy from? Germanium.
The sun.
Okay, continue.
The sun is heating the particles, and the electrolyte, the B, is like allowing the heat to travel better.
Okay, no. I wouldn't say it's allowing the heat to travel better, but what? So the sun, yes, and also can some of you give me other sources of heat, maybe besides just the sun? Let's go ahead and go to
the energy released from the sun.
Okay, that would still be the sun, though. I think that would be kind of in that same category. Let's go to polonium.
When people walk on it, it would create friction.
Okay, it's true. You could have some friction there. Not exactly what I'm looking for, but let's try moscovium again.
The heat from the ground.
Thank you.
Travels up.
Yeah, from the ground and from
the sun.
Yeah, like our air, right? The atmosphere, it's got tons of energy. It's got all these particles moving around that have energy, right? And so we have a lot of that as well. Thank you, Fluorovium, for adding that in there as well. So we are getting energy from all over the place. Do you have a question or a comment to add on to that?
Is it because like the atmosphere has so many particles? Is it related to collisions in a way?
Okay, so yes, the atmosphere's got lots of particles. They're colliding into the ice, right? And so that's giving energy for it to melt, right? So what then is the reason for it melting in front of us? Is the energy from around side? What we don't see is we don't see it being able to come back together. Right? So remember that normally in a situation where you have freezing and melting happening at the same time at your melting point or at your freezing point, you've got the equilibrium, right? Some particles are recrystallizing, some particles are coming apart. You've always got the freezing and the melting taking place at equilibrium. And so what we've done by adding salt is we're allowing the normal process of melting to take place, but we aren't allowing the process of freezing to happen anymore. And so it starts to just turn into this puddle, right? It turns into this liquid, which it would normally do, and then also then refreeze. But now it's not getting a chance to refreeze because these particles are getting in the way, and so they can't grab hands anymore. And so the energy from the environment, the sun, the ground, the air, etc., that's all melting, and it's always melting it, right? But you also have the refreezing that takes place. But in the case of extra particles, extra solute particles getting in the way, then you don't have the refreezing taking place. Isn't that pretty cool? It's kind of nice, huh? So it's wild to think about these things and how all of this stuff is involved and you don't think about, but in chemistry, it just makes you see all the stuff that you don't normally get to see. It's so cool. All right, any questions on that? Okay, so let's talk about boiling point elevation. Okay, so that was freezing point depression. Similar processes are happening in the boiling point elevation. Obviously, you are going to have some issues with solute particles getting in the way of bonding. Intermolecular forces are going to stop the intermolecular forces a little bit. But actually, we have to kind of focus on the other part here if we want to talk about what's happening in terms of vaporization. Because that vaporization is the process where you're escaping. Notice in this picture, we have a lot more escapees than we do in this picture. And the reason that we have more escapees is because these little guys, as they try to get away, the little water particles, they might end up bouncing into and running into our solute particles. And so if they're getting in the way, these solute particles are getting in the way, then they, even if they had enough energy where they would have been able to escape before, now they don't have the energy to get out like they did before, okay? Because they're bouncing into these other particles. Now, when I was young, my grandma would tell me, hey, add salt to your water when you're cooking your noodles because that's going to make them cook faster. Let's talk about whether that might be true or not. Has anybody ever been told that before? Raise your hand if you have. Anybody? Okay, a couple of you, yeah. And so I was like, okay, well, that sounds good. And I would add salt to my water. But of course, I didn't ever do any experiments on it. Now, I did eventually when I got older. But when you add salt to water, the boiling point elevation with a small amount of salt is so little that your temperature rise is going to be very little, so that it doesn't really affect your cooking time much at all. Okay, not anything that would be significant. I don't know, maybe a second, 2 seconds, who knows, right? We'd have to do some experiments on it. If you did want to actually make it so it would cook it faster, where it would be a significant amount of time save, then you would have to add so much salt to it that it would be like the nastiest, saltiest noodles you've ever eaten. You wouldn't be able to eat them. They would be so nasty. Okay, so adding salt to your water does not really elevate your boiling point by anything that would be significant if you're just talking about what you do by tossing a little salt in your cooking water. Okay, but it does elevate it. It's just a very small amount that you probably wouldn't even really be able to measure with a normal thermometer. But if you really wanted to add a lot of salt, you could see that boiling point rise up. And then it might change your amount of time just a little bit. Okay? So those particles are getting in the way, and the more solute particles you add, the higher the boiling point is going to get. And it's, again, because you need more energy in order to vaporize it, and so that therefore you would need a higher boiling point to vaporize it, and that's a higher temperature. Questions on that one? Okay. Then we have the electrolyte versus the non-electrolyte. What's happening if I put an electrolyte into water versus a non-electrolyte? Let's start with our first one. This is sucrose, C12H22O11, and that is being put into water. And when I put it into water, you can kind of imagine kind of like a little bit of a sugar cube that you might have. And that sugar cube is going to break up into tiny little pieces, right, of sugar. But each of those little pieces of sugar is still a C12H22O11 by the time it all gets broken up. And so for every mole of solute, let's say I have 1 mole of solute here. For every 1 mole of solute that I put in, I am going to get 1 mole of solute particles. Notice the word particles there. That comes out. Okay? So if I take sodium chloride, however, looks the same, little crystal, right? Got a white crystal here, and it's going to break up into small pieces. But these little small pieces now that it breaks into can actually break up into even further pieces of sodium, Na+, and chlorine, Cl-. So my sugar didn't break up into any smaller pieces than the entire molecular structure, even though it seems like it could break up into a lot. However, my chlorine and my sodium actually broke up even further. And so I get, for every 1 mole of solute, I get 2 moles of solute particles. So I get more particles from an electrolyte than I do from a non-electrolyte, because non-electrolytes are molecular compounds and they stick together. Now, if I take calcium chloride, CaCl2, and I put that into water, now I'm creating 1 mole of calcium ions and 2 moles of chlorine ions, which means I'm creating 3 moles of ions. So I have got way more particles from calcium chloride than I do from sodium chloride, and more than, of course, from the sucrose. This is why you put magnesium chloride, very similar formula, right? MgCl2. Magnesium chloride on your streets, especially when it's going to be an even colder day, than just salt. Salt will lower the freezing point a little bit, but something like mag chloride will lower it even more. And if you can break it up into even more pieces, you're going to lower that freezing point even more. Question?
If you use magnesium chloride for pasta instead of normal salt, would it have like a greater effect?
Yes, it would have a greater effect. Would it be enough to see a temperature change that would be significant? No. Yeah, you just need so much.
Or a lid, right?
Okay, yeah, lid's another way to do it, but that's another subject matter. That's another way to do it, right? Okay, so questions on that? More particles is going to give us a better freezing point depression. Okay, let's now look at this. We have 2 questions. These are going to be turn and talks. Okay, which concentration of sugar water would have the most extreme colligative properties? And then you got some concentrations there. And then 2, consider the following 1 molar solutions of sugar, sodium chloride, and calcium chloride, which would have the most extreme colligative properties. So let's see if you can answer those questions. Turn and talk, and I will call on some of you.
That's what we literally just said.
I would say
You mind,
NaCl from because sugar is less soluble.
All right, let's see what we've got. Thallium, what do you think the answer is for the first one?
1M.
Okay, why? Okay, she said 1 molar, but not exactly sure why. What about arsenic? What do you think?
We also said 1 molar, but it's because like the higher the concentration, the more extreme the properties become.
Yeah, so is this more higher concentration?
Yeah.
How much higher?
A lot higher.
Than this? Like, could you give me a number?
It's like 10 times more than that.
10 times more concentrated, right? This is a mole per liter. This is 1/10 of a mole per liter. So yeah, this one is definitely going to be more, going to have a bit. Excellent. Okay, let's go to our next one. Next question. This is going to go to tellurium. Pass it on over.
I'm gonna take a guess because I'm not sure.
Okay.
I think maybe sugar.
Okay, why?
Because I think it has the highest concentration.
Okay. It says that they're all at 1 molar concentrations. Not sure? Okay. Good. And I'm going to just do somebody by random. Calcium. Going to work our way to the other side of the room real quick. All right. What do you think? Calcium.
Like calcium chloride.
Because?
For like 1 mole of solute, there's gonna be like 3 particles for it.
How many particles is it going to break into?
3.
3 particles. Yeah. It's going to break into 3 particles here. And so this is going to have a bigger concentration. 1 calcium, 2 chlorines. This one breaks into 1 sodium and 1 chlorine. So that's 2 particles. This one doesn't break into smaller particles. It stays together as a big clump. It's a molecular compound, non-electrolyte, so it doesn't break into smaller pieces. Good job, everybody. So let's look at what we've learned. Today, we've gone over our objectives that basically asked us to figure out what non-electrolyte effects would be compared to electrolyte effects, right? Non-electrolytes do not have as much of an effect as an electrolyte, okay? The electrolytes break up into pieces, into ions, and so they have a bigger effect. And then we looked at the freezing point depression and boiling point elevation, and we saw that there's reasons that is involved with that include intermolecular forces being interfered with and the obstruction of something escaping. Now, before we finish, I want to talk briefly about your worksheet that you've got. That worksheet that you've got is going to ask you to solve dilution problems. And I want to show you the formula you're going to use for that. It's a simple formula, okay, but it is formula that you need to solve these problems. It's M1V1 equals M2V2, okay? Which basically means the molarity and the volume of the first condition is equal to the molarity and the volume of the second condition. So if you look at your dilution worksheet, you'll see a question, for instance, like number 2. If you dilute 4.5 liters of an 8 molar solution down to 5 molar, how much new solution can you make? You're going to plug those values into this formula and you'll solve for it. Okay? Thank you.